Okay, anybody have any homework questions? Yep. From structures? Okay. Ooh, I must have an old list because my only goes up to 9. Anybody have structures with them? No deal. Oh yeah. Oh, I like it. I would have thought you did that as an artistic choice. Okay, so why don't I? Okay, yeah. Let me just draw the free body diagrams of each of the members. I think that'll probably help straighten up how to approach this. So let's think of. So this is. Structures number 10. And it looks like this. There's a member this way. One this way. One that way, and these are all connected by pin points. And then there's a pulley centered at this pin. And it connects a cable to there and applies a downward force of 3,000. And it calls the joints A. The connection with the cable is B, C, D, and E. And then the members are 1, 2, 3. And you can do it that way, but I'm going to also call the pulley number 4. And there are no weights. This is a frictionless contact at E. And now I'm just going to go through the free body diagrams. Okay, so member 1 looks like this. Down at A at the bottom, we're assuming the pin is part of member 1. And so we have the force applied to 1 by 2. And we also have the reaction with the ground. I'll call that RA. And then up at the top, we have the connection between 1 and 3. So this is F1, 3. And then we have the cable force here. I'll call that, well, that's a single cable going over a pulley. And we're given the force of 3,000. So we know this force is 3,000. And now I'll go on to 2. Down at the joint A, 2 is only touching the pin, which is part of member 1. So this is negative F1, 2. And then the pin at the top is part of member 2. So we have the force on 2 by 3. That pulley is also connected to that pin, so we also have the force on 2 by 4. And those cable forces don't show up. If you made the pulley part of member 2, yes, then they would show up, and you can do it that way too. Yeah. And it'll save you some equations. To me, this way is a little more intuitive, but yeah, that works fine. And now, Freebody diagram for number 3. Down at the joint E, this is perpendicular to the surface. So I'll call that the scalar RE with a known direction. We can figure out the unit vector. At the midpoint, it's only making contact with the pin. So this is negative force on 2 by 3. And then up at the top, this is the force on 3 by 1, so negative F13. And then last is the pulley. In the middle, is the force on 4 by 2, so that's negative F24. And then a 3,000 Newton force this way. And a 3,000 Newton force this way. And now you can solve it. Any other questions about that one? What are the internal loads for member 3? Oh, the internal loads. Okay, okay. Oh, internal loads. All right. Yeah, I did not talk about this, did I? The external loads. Oh, that wasn't really supposed to be on here yet. That I moved that problem over. Yeah, but let's talk about how to do it. I'll talk about it sort of more formally pretty soon. So once you calculate the external loads on member 3, anybody have numbers for those? So dot, 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 and you'll get a free body diagram of member 3. That looks like we'll have a force vector here, a force vector here, and a force vector here. Okay, sure. Even if they're wrong, we'll use it. Mm-hmm. Point 13355.1. And is this F13 or negative F13? Okay. And then the middle one? Yeah. Okay. Okay. Yeah, RE. And can you multiply that for me by cosine and sine of 70? It could be one of you other deadbeats to do it. Okay. 2099.1. Yeah, 0.1. All right. So to come up with internal loads, so now we want the, and we're used to calculating the internal loads on beams that are lying flat, right? But really don't think about it as the beam lying flat. That's how we always look at it. We do internal loads with the x-axis pointing along the beam's axis. Whether it's lying flat with the x-axis along or whether it's tilted like this and the x-axis is along the beam axis, that doesn't mathematically make any difference to us. That just has to do with how crooked our spines are. You know what I mean? Like once we get the x-axis oriented with the long axis of that beam, now to get it horizontal, just turn your head a little, you know, and you're good. So we want to go from, so we want to re-express these forces. We want to take these force vectors that are currently expressed in this coordinate system and re-express them excuse me, we want to re-express them in this coordinate system. Okay? And to do that, we're going to use a rotation matrix. Rotation matrices are the coolest thing in the world. It's not really the traditional way to do this kind of stuff because traditionally people didn't have calculators in their backpack at all moments that would do matrix calculations for you. But, you know, now we have it. So let's use rotation matrices. So, okay, so here's how you do it. If you have a vector, so say you're given a vector u old in an old coordinate system, to re-express that same vector in a new coordinate system that's rotated counterclockwise an angle theta from the old coordinate system, U new is going to be equal to this matrix Q times U old, and the rotation matrix Q is cosine of theta, sine of theta, negative sine of theta, cosine of theta. And if you had to type that in every time, that would be sort of a nuisance, but it's really easy in all these calculators to enter a program that just lets you. And I think actually, if you look in the course materials section of D2L, I think I have a list of the small amount of code it takes to enter programs like this, so that you can just call up the program, enter in the angle, and it just makes the matrix for you, and then you just multiply by your vectors. And you don't even have to know how to do matrix multiplication or anything like that. Your calculator will do it for you. Just use the regular multiplication symbol. Yep. Yeah, that would mess it up. Well, that would move it the opposite direction. That's interesting that you asked that. Have you seen it before with it in the top right? Okay, so what's going on is this, and it can be very confusing. Half of the people do rotations as a rotation of the coordinate system with the vector staying constant, and half of the people do it as a rotation of the vector with the coordinate system staying constant. Okay, and those have the opposite effect. If you can you picture what I'm talking about? They're exactly opposite each other. Like if you so if this is your vector and you re-express it in a new coordinate system like this, okay, say this angle is theta, okay, the components you get for that vector are exactly the same components you would get if you kept the coordinate system the same and rotated the vector clockwise by that angle. And that's where that negative comes in the opposite place. It's a pain in the butt. The one we're using changes the coordinate system, not the vector. And that's how I always do it. And so if you're taking more classes with me, you might want to get used to that. It's totally your choice, but I would recommend that you always do it one way or the other. You can, any task you want to do, you can do it either of those two ways. Just don't go back and forth because you'll drive yourself crazy and you'll never remember the rules, and you know what I mean? Just do it one way every time. A reflection, I never do reflections because it doesn't really work with, reflections don't work with, at least the calculations I've done with vectors. Yeah, it's never come up, but I'd have to think about that. All right, so here's our rotation matrix. We're going to come up with the rotation matrix, and then we're going to multiply it to each one of these force vectors. Do we know the angle of that beam off the top of our head? It doesn't give it, does it? Okay, so we'd have to figure it out from, we have to make a right triangle out of that, and well, that won't be so hard. Let's see. Let's see. So we know that the height is 0.6. and the width is 1. And so this angle, I'm going to call it phi, actually. So this angle phi is the inverse tangent of 0.6 over 1. And what do you get for that? 31 degrees. And now we have to think, do we want to rotate our coordinate system clockwise or counterclockwise? Clockwise, yep. And so our theta, so we want a clockwise 31-degree rotation of the coordinate system. So our rotation matrix is cosine of negative 31, sine of negative 31, negative sine of negative 31, cosine of negative 31. Can someone give me the cosine of that and the sine of that? .857. And then what sine? Negatives. It should be positive sine of negative 31 should be negative, right? So tell me the value again. And now one by one, we're just going to multiply our old force vectors to this to get the new force vectors. So 0.857, negative 0.515, positive 0.515, 0.857 times 3355.1 1829.1 and that's going to give us our new force at the left end. Anyone know how to enter those in? So every TI calculator does it a little bit differently, but by the way, these matrix calculations are the reason that I like to use this as my vector notation, the vertical, the column matrix like this. Other people use other notations, but when you're doing matrix calculations with vectors, this is how the vector is arranged as a matrix. Yes, that's the sign that it's a matrix. I call it under squiggle. Yeah. Okay. Okay. And then we're going to multiply that same matrix by the force in the middle. So negative 4114.9 negative 3929.1. Okay, so can you multiply those? Okay. 5486. And then I guess let's do the last one. So the last vector, 764.1 and 2099.1. Okay. 2,192. Point what? Okay, so okay, good. That's true. Yeah. Okay, so what this means is now we have an internal loads problem where on the left we have a force of 1933 3295. In the middle, we have a force vector of negative 1503, negative 5486. And at the right end, we have a force vector of negative 426.2, 2192.4. And now it's just a simple internal loads problem. But the very short answer is I didn't mean for B to be there in this problem. So you can skip it. This rotation matrix thing, though, is going to be so useful. It's kind of, I think, often sort of de-emphasized in classes, but then when you put the stuff from classes into practice for real research projects or, in a real work environment, you have to use it all the time. That was my experience. And, in like one place you could use this is in physics 1, when you did inclined plane problems with like friction and stuff, you would always use the rotated coordinate system to simplify some of the stuff, but it complicates the weight force, So you could use this idea if you have time and inclination, try it on a problem or two. Go back to a physics 1 inclined plane problem and think of it as a issue of like rotating the coordinate system. So if you have something like this, where this is 20 degrees and you have a block here, Okay. Well, in this coordinate system, the weight force, it's straight down, right? So the weight force is 0, negative mg, right? Now in this coordinate system, you want to know the components. Well, what you've done is rotate this. This is a rotation of negative 20 degrees, clockwise 20 degrees. So now just multiply cosine of negative 20, sine of negative 20, positive, sorry, negative sine of negative 20, cosine of negative 20, times your original components. And it gives you negative mg times sine of negative 20, negative mg times cosine of negative 20. And just like that, you don't have to think about the trigonometry or anything. Just think about how you're changing the coordinate system. Okay, well, let's go back to internal loads. And now we've talked about how to do any kind of problem where the only loads are point loads. So the problems so far have only had external point loads. So now let's think about what happens when the external loads are distributed loads. Okay, so I'm going to start out with an example where I'm going to go back to just calculating the internal loads at a single spot. I'm not going to calculate it in terms of, as functions of x. Okay, so let's say that we have a cantilever beam. And let's say that it has a mass of 50 kilograms. And a triangular distributed load with a maximum value of 10,000 newtons per meter. And let's say that the length of this beam is 2 meters. We want to calculate the internal loads, let's say half a meter from the left end. Okay, so we're going to make our cut where the piece that we're considering has a length of half a meter. And the loads that are applied to this are a part of this distributed load. But notice if I draw in all the stuff that we're skipping, we're missing a lot of this distributed load, most of it. Okay. And we're missing the external loads at the wall, which is a couple and a force vector. And we also have a weight force. That weight force is going to act from the center of mass. And then we have the internal loads. And so notice that we're going to have to figure out, like, for example, this triangular distributed load all the way over at the right end of the beam has a value of 10,000 newtons per meter. But where we're making our cut, the height isn't 10,000 newtons per meter, it's something less than that, right? And the weight doesn't deal with the weight of this piece that we're skipping. It only deals with the weight of the quarter piece we have. And it acts at the center of mass of the quarter piece we have, not at the center of mass of the beam. Okay. So notice if we would have applied the weight force and the distributed load where we apply them to isolate the whole beam, they wouldn't have even shown up in this free body diagram. Okay, so because we would have put the weight force acting at the center of the beam, we would have put the triangular distributed load 2/3 of the way this way on the beam, and we would have thought, based on that, there were no external loads acting. Well, we'd be wrong, we'd get the wrong answer. So the bottom line is, for any distributed load, and now we have to think of weights as distributed loads. So including weight, you can't represent it as a point load until you choose the body to isolate. Okay. So the way we're going to think about this is the weight, instead of thinking of it as a point force acting at the center, it's a uniform distributed load. So the weight is a uniform distributed load with a magnitude that's equal to mg divided by the length of the beam. Okay, so let me draw this free body diagram again. So here's the piece that we're isolating. Here's all the stuff that we're not isolating. And we're including part of the distributed load that represents the weight. We're skipping all of that over here. And we're representing part of the triangular distributed load that represents that given load. We're skipping all this over here. And then we have tension, shear force, and bending moment. And now that we've chosen the body to isolate, now we can represent these distributed loads as point forces. Okay, well, if we go a quarter of the way from the left to the right, what's the height of the distributed load? It's a linear function, you know, it's 10,000 at the right, 0 at the left, so this has to be 2,500 newtons per meter. And what's the magnitude of the uniform distributed load representing the weight? That's 50 times 9.81 is the weight, divided by 2. So that's 245.25. Yeah, divided by 2. Yeah. Okay, and now we have all the values we need to put this stuff, to write this stuff as point loads. So let's think about the triangular distributed load. We have a height of 2,500, a width of 0.5. So the area of the triangle is 0.5 times 2,500 divided by 2, so that's 625. And the centroid is 2/3 of the way from the left to the right. So okay, and so we're going to represent that part of the total distributed load as a 625 Newton force acting 0.3 repeating from the left end. And then we'll do the rectangular one. Well, that's going to act at the midpoint. So this is just going to be 0.25. The base, again, is 0.5. The height is 245.25. So the area of the rectangle is 122.625. And now I'll draw my last free body diagram of this piece. So we have a weight force in the middle of 122.625. We have a downward force of 625 at a distance of repeating from the left end. And then we have our internal loads. And now Newton's second law says 0, negative 625, plus 0, negative 122.625, plus T negative V is equal to zeros. And so T is equal to 0. V is equal to 747.625 negative. And then the moment equation. There's a moment from the 122.625 with a moment arm of 0.25. Does that make it rotate clockwise or counterclockwise around the left end? The 122.625. Clockwise, so that's negative. And then there's a moment arm of 0.3 repeating for the force of 625. Does that make it rotate clockwise or counterclockwise? Clockwise, so that's another negative. Plus m minus v times the moment arm of v is 0.5 is equal to 0. So m is equal to 0.5 v plus, can someone multiply and add those two numbers together for me? $3,273.75. Okay. And then the last thing we have to do is substitute V in. And what do you get for a final answer for the bending moment? $2,900, like exactly. and that's in Newton meters. Okay. So, just like when I did the first internal load calculation with point loads, I first did it at some finite location. And I said, if you get confused about how to do this, once you start generalizing, coming up with functions of x, go back and compare it to that first case we did where we did our cut at a finite spot. So it's the same thing now with distributed loads. So now we're going to do it for general values of x, and it's going to get to be sort of a pain, okay? But if you get confused about it, go back to this first example that I just did at a finite location for x, because all of the ideas are the same. It's just that we're going to switch to functions of x now instead of finite values. Okay. All right. So now we're going to do the same problem, but we want to find the internal loads as functions of x. Okay, well, we're going to start out we have this beam, and we have some reactions over here, but we don't know what they are. So I'll call that R and MR. They never come into our cuts, so I'm just going to leave those alone. And then we have a distributed load representing the weight. The magnitude of that distributed load is, what do we say, 245.25 Newton meters everywhere. And then we have this triangular distributed load with a maximum value of 10,000 newtons per meter. And one thing that we're going to need for every one of these distributed load problems is to represent the distributed load as a function of x. So let's just do that now. So let's determine the magnitude of each downward distributed load as a function q of x, lowercase q. Okay, well, it's easy for the weight force. I'll call that qmg as a function of x. That's uniform, so that's just a value of 245.25, no matter where you are. And then q for the triangular distributed load as a function of x is just the function representing that line, right? The height of that line is the magnitude of the downward distributed load at any value of x. So we just need to come up with, this is going to follow mx plus b, where at the left end, x is equal to 0. At the right end, x is equal to 2. So first of all, what's the y-intercept? 0. Stop me if you have any questions. And then the slope is the rise over the run. The rise it rises from 0 to 10,000. The run is 2. And so this distributed load is 5,000x. Okay, so for any x value, that's the magnitude of the distributed load at that point. And then I've mentioned this function q before. The total function q, we'll use this later, is just the sum of these two. And so it's equal to 5,000 plus 245.25. I'm just setting this aside for later. Okay, so now we have to find the spots. We're almost ready to make our cuts. We have to find the spots where the free body diagram changes qualitatively. So the rules for those are endpoints, point loads, and then places where the distributed load functions change. You can see here, we can represent these distributed loads with the same functions the whole way. So the distributed load functions don't ever change. And so the only points we have to worry about are the two endpoints, which means we can just make one cut. We just need one cut that represents all the points between the two endpoints. Everyone with me on that? So our cut 1 is for x values from everywhere from 0 to 2. And we're going to start at the left endpoint and go to some value x. This distance is x. And I'm going to draw the distributed loads one more time. So I'll have to do one more free body diagram for this cut. But we have the downward distributed load of 245.25. And we have the triangular distributed load and now there's sort of a potential issue. When we knew that we were cutting off only a quarter of that piece, we could figure out how high that triangular distributed load went. But now this x could represent anywhere in that range, and so the height is going to vary. And so we're going to have to represent the height over here in terms of x. Anybody have a feel for what that height is going to be at a given value of x? Yep, 5,000x. Because that's exactly what that linear function says. Choose an x value. That's the height of the distributed load. So this one is this is QMG, and this one is the Q for the triangle. And then we have the internal loads. And now we can think about these shapes again. So we have a triangle with a base of x and a height of 5,000x. The centroid is going to be 2/3 of the way this way. That's just going to be 2x over 3. And the area of that triangle is 5,000x times x over 2, so 2,500x squared. So that's the point load that represents that triangular distributed load. And then we'll do the same thing for the rectangle. It has a height of 245.25, a base of x. The centroid is right in the middle. So this distance is x over 2. And the area of the rectangle is just x times 245.25. So 245.25x. Now I'll do the free body diagram again. So there's our cut. From the middle, we have the point force representing the rectangle, 245.25x. 2/3 of the way along, we have the downward force representing the triangle. That's 2,500x squared. And then we have the internal loads. And this distance is x over 2. This distance is 2x over 3. And now we can calculate the internal loads, and we're going to get functions of x for everything. Any questions about that yet? So Newton's second law says 0 and then a downward force, so negative 245.25x. Plus 0, negative 2,500x squared. Plus t negative v is equal to zeros. So t is equal to 0 for the whole thing. But v is equal to negative 2,500 x squared minus 245.25x. And now it's going to get a little uglier for the moment. So the moment equation, we have a force of 2,500. Well, let's do the weight first. We have a force of 245.25x. And what's its moment arm? It's over 2. Our about point is over here. And is that clockwise or counterclockwise? Clockwise, so negative. And then what's the moment arm for the 2,500x squared? 2x over 3. And that's clockwise too, so that's another negative. And then plus m minus vx is equal to 0. And so we get m is equal to vx plus, I think that's 1666.6 repeating x cubed plus 122.625 x squared. And now we'll substitute in the function v and multiply, we're going to multiply that by x. So m is equal to negative 2500 x squared. No, multiplied by x, so x cubed. Minus 245.25 x squared plus 1666.6 repeating x cubed plus 122.625 x squared. And we can group the like terms. So we end up with this function m that's equal to negative 833.3 repeating x cubed minus 122.625 x squared. And now, because there are a million places you can make mistakes in a problem like that, we're going to do our checks. So I'm just going to do the derivative checks. But here, like the troubleshooting relationships. First, dm dx is supposed to be equal to v. Okay, so dm dx is negative 2500x squared minus 245.25x, and that's equal to v. So that one works. The second one says dv dx is negative q, and this is where we're going to go back to that q that I set aside. So dv dx is equal to negative 5,000x minus 245.25. Negative dv dx is 5,000x plus 245.25. Go back up to that q that we found earlier, and it matches. Cool, right? No. Yes, it is. 3, 4, 5. These are the endpoint conditions. I'm not going to do that right now, but Any questions about that? Well, I've given you a lot to think about today. That's a lot. But I mean, it's, there's so much stuff that comes up over and over again that after you do a few problems, it'll just start to be like, okay, this, same thing again. This is a little different, but it's the same in this way. So um, it's just going to take a bunch of problems. And on Thursday, I'll go through a few more examples. If we get far enough into examples that I've done, maybe we'll take some time and do some problems in groups so you can sort of work together on it. Okay. Any questions? All right. See you Thursday.